All right, we're going to change up a little bit and go testing a claim about a mean. We've been working on proportions for a long time, and now we're going to go means instead. When theta is not known, when baby sigma is not known, when sigma is not known, or the population standard deviation is what it stands for, we can use a t-test. And to be honest, that's almost all the time. Very rarely will we ever know what the population standard deviation is. So most of the time with means, it's going to be a t-test instead of a z-test or normal distribution. Notation you need to make sure that you know in a sample size as always, x bar is a sample mean, mu with sub x bar is going to be population mean, or just mu itself will be population mean. Requirements, here's what has to happen before we can do the test. Number one, the sample has to be a simple random sample as always. And number two, either or both of these conditions are satisfied. The population is either normally distributed or the sample size is bigger than 30. Then we go with central limit theorem that says sample size bigger than 30 is normally distributed anyway. Test statistic, this is what the t-stat is x bar, or the sample mean, minus the population mean over sample standard deviation, which is s, over square root of the sample size, which is n. Running the test, we're going to do p-values using our t-distribution. Degrees of freedom, remember, are n-1 until you're told otherwise. Critical values, also use student t-distribution. Degrees of freedom, n-1. Okay, so we're going to do both p-values and critical values, but count more because they're going to give you the same result every time. Important properties. Number one, the student t-distribution is different for different sample sizes. It approaches normal. The bigger the sample it is, the more normal it approaches. Has the same general bell shape as a normal distribution. Its wider shape reflects the greater variability because you're using the sample standard deviation to estimate baby sigma, which is just it's not a great estimator. Number three, the student t-distribution has a mean of t is 0. The standard deviation of the t-distribution varies with the sample size and is always greater than 1. So that's what's different. With the normal distribution, the standard deviation is always 1. And when you get to a t-distribution, it varies. Number 5, as the sample size gets larger, t-distribution gets closer to the normal than a minute ago. Example, really watch this part of it. I think this will explain a lot. Listed below are the measured radiant emissions corresponding to radiation emissions corresponding to a sample of cell phones. Use the 0.05 significance level to test the claim. Here's the claim. The cell phones have a mean level that is less than 1. So that obviously, since it says less than there, that's going to be the alternative in a second. Here's all the radiation levels that they measured. The summary stats for those measures, there's x bar, which is a sample mean. There's a sample standard deviation. And you can get those two numbers just by plugging those into L1 in your calculator. Go to OneVer stats, and it will give you both of those measures. Continuing, requirement check. We assume the sample is a simple random sample. And number 2, the sample size is n is 11, which isn't big enough. It's not greater than 30. So you must check a QQ plot to see if it's normal. We're going to do that on the next slide. There's a QQ plot, and I drew a line through there, and you can tell it's fairly close. So we're going to say, okay, it is from a normally distributed population because a QQ plot is fairly close to a line. Step 1, the claim was that it was less than 1. The alternative claim would be greater than or equal to 1. So here we go. Our HO is going to be the mu is exactly 1, and the claim was, or the alternate hypothesis is the population mean is less than 1. So that's what we're going to test. We have a 0.05 significance level because it was less than 1. Because it's about a mu, the most relevant stat would be the sample mean. So that's what we're going with, the sample mean. We got to calculate our test stat and find a p-value. So the test stat, you have this form a minute ago. There's your sample mean, there's your population mean as we know it. There's sample standard deviation and square root of population, and it gives me this number. It gives me negative 0.486. That is my test stat. All right, when I graph that, I do the graph here. So it's the critical value method, which is what we're using because the test stat is negative 4.86, which if you look at it, it's right there. That's where the test stat falls. This is the rejection zone where you reject the null. And because it's not in there, we would fail to reject the null. All right, the p-value method, step 7, using our calculators. The calculators would tell you the p-value. We've done that, quite a while now. It says the p-value is 0.3191, which is much bigger than 0.05. So even with the p-value method, we still fail to reject the null because the p-value is too high. The p-value would have to be below 0.05, as you know by now, and it's way too big. Step 8, because we fail to reject the null, we conclude that there is not sufficient evidence to support the claim that cell phones have a mean radiation level that is less than 1. Because we failed to reject the null, which was it was 1. If we're not going to reject it, that means you can't say it's less than that because we're not rejecting it. All right, assuming that neither software nor TI-83 Plus calculator is available, use table A3. We have them available, and so we're not going to worry too much about this. And that was a left tail test, obviously, because it was less than. And if I slip back there, I should have pointed this out on that slide, but those were the T-scores that were found on that picture a couple slides back. And really, guys, that's it for today. Very similar to proportions. Different way to find your test stat, a little bit different way looking at it. We're doing t-distribution instead of a normal distribution because we're finding means instead of proportions. Hope it makes some sense. You're getting better and better at this, and I think you're going to get even better. And pretty soon you'll be like, this is no big deal. So I'll see you tomorrow. We'll work on it like we always do. See you then.